All right, good morning. Apparently, this lesson didn't get saved from last year, so I have to do it again this year. This is the beginning lesson on motion in one dimension, which is what's in chapter 2 of your textbook. So you're going to need to be reading chapter 2, and I'm going to give you the background here, and we're going to talk about a few things, and we'll get to the meat of the matter in the next lecture. So we're going to study motion in one dimension. Motion in one dimension. Now that means motion along a line. And the reason that's important is it only needs one variable to keep track of position. So if you moved along a plane, you would need an X and a Y in 3 dimensions, an X, Y, and a Z up and down. But in one dimension, you only need an X to keep track of things. Now, this doesn't necessarily have to be a line, but definitely a number line is the most basic thing that we can think about that goes, here's 0 in the middle, and we got positive numbers to the right, and we've got negative numbers on the left, +2, -2, that kind of thing. Yeah, so that's definitely what we need. Motion in one dimension, we just need one number to keep track of where you are on this number line. But it could also be something like a sidewalk outside your house, right? That's something more concrete. We could have a bunch of different blocks of cement, and maybe your house is right here. And so we say that if you go this way, we're going in the positive direction, and we count the number of little cement blocks, and this way might be the negative direction. That'd be a more concrete, literally, example. But even something that curves, like a monorail or roller coaster, could be kept track of because you're stuck on a track. You just need one variable to keep track of how far along the roller coaster you are or how far along the monorail. Now, with roller coasters, there is that issue that they wrap around, they come back to the station. And so we might have to deal with that. That's a little different than a number line that goes infinitely far in each direction. Monorails, I mean, the monorail in Vegas is just has limits. At one end, there's a I don't know, MGM Grand Hotel, and on the other end is the used to be the Sahara, now it's the SLS. So what are you going to need to do to do this? Well, let's make a little table of what we're going to keep track of. There's the thing, there's the variable, um, there are the units for the variable, then there's other info that we might want to say about it, okay? So this is going to be like a table. And the first thing you need to keep track of is the position of whatever you're keeping track of. The variable we're going to use for that is the letter X, and it will be measured in meters. Now, I use square brackets whenever I'm talking about meters. I'm sorry, whenever I'm talking about units in this class. So square brackets around the M means the units for X will be meters. Info, well, the info about this is we need to consider the origin. You probably should tell somebody where the origin is so that they know if you say, hey, 3 meters, 3 meters from where? Also, this could be plus or minus, which indicates the direction. So as we had in the sidewalk example, positive on this side, negative on this side. In the number line example, positive on this side, negative on that side. So there could be a plus or minus on the number to indicate the direction. The next thing we're going to keep track of is displacement, because now we're talking about movement. Displacement gets the variable delta x. Delta means change in science, and the units will be meters again. This one is independent of the origin, but I will define that delta x is there should be an equal sign in there, is a final position minus an initial position. These subscripts indicate specific positions. We could use position 2 minus position 1, or position 100 minus position 99, but this one can also be plus or minus. So this is I'm sorry about that equal sign in there, looking kind of crappy. Is it worth fixing? No. So displacement, the change in position, is delta x. The next thing we would do is keep track of time. And this is the elapsed time. We don't want the time of day. We care about how much time has gone on during a process, and that will be measured in seconds, and that gets the letter T. I use a little scripty typewritery type of T because if you just make a regular print T, it can sometimes look like a plus sign, and that isn't very good. This one does not depend on an origin or anything else, but this is positive only. Time only goes forward. Elapsed time only goes forward. I believe your book uses a delta T. I think it's okay to drop the delta. Remember, delta means final minus initial. And if we're going for elapsed time, you could imagine that we're using a stopwatch. And so the initial time will always be a 0. Okay, into the meat of the matter, we have a new thing we can define called velocity. Velocity is very much akin to speed, and it gets the letter V. Velocity will be measured in, and it looks like I'm having a diagonal line here, meters divided by seconds, or meters per second. And that's because velocity is defined as the displacement divided by the time. This is the most basic thing you can do. How far did you go and how much time did it take? That's an indication of how fast you're going. That's why I say velocity is like speed, but velocity is better than speed because velocity can be positive or negative, which indicates direction. It's the same positive or negative that the displacement is. Just down here, divided by something that's always positive, it's going to be the same positive if this is positive, negative if that is negative. And it indicates the direction. Are you moving to the positives? Are you moving to the negatives? Now notice you could be on the negative side of the sidewalk and headed to the left, and you would have a positive displacement. You would have a positive velocity at that point. And finally, we can do that again. We can define something called acceleration, which gets the letter A. Now I use a script type A, a typewriter style A, because once again, if you make a normal print A, it might look like a 9 if you go fast. I've done that before. This is measured in meters per second squared, which is also the same as meters per second, because acceleration is a change in your velocity divided by time, and it too can be plus or minus, indicating direction. Now, it's kind of interesting to think about the direction of acceleration because, like I said, you could be on the negative side of the sidewalk or the negative side of let's do the number line for this one. You could be on the negative side of the number line. You could be moving to the right. You would have a positive velocity. But if you were slowing down as you did it, if your change in velocity was a negative number, then the acceleration could be negative. So you could have a negative velocity, negative position, positive velocity, and be slowing down with a negative acceleration. That's all legal. So the acceleration means what's happening to your velocity. Are you tending to go more this way, or are you tending to go more that way? It's a trend. In fact, these things here, displacement divided by time, and velocity, change in velocity divided by time, these are rates of change. I should probably use the contrasting color real quick here. And so these are rates of change. This one in particular, really popular with cars, right? We want to know, hey, what's the 0 to 60 time? 0 to 60 time. So if I go 0 to 60, which is a known change in velocity, and it's a positive change in velocity, we're speeding up. Then we do that in, say, 3 seconds. By dividing by 3, that's going to give us 20. That's a big number for acceleration. If I go 0 to 60 in, say, 20 seconds, like my old Volkswagen bus used to do, then this is only going to be a number of 3 or a smaller acceleration. So that's how they tell you the acceleration of the car. They tell you 0 to 60 time. So sort out for yourself what the positive or negative means for displacement, velocity, and acceleration. Also know that these things are rates of change and that we're going to keep track of these variables: position or a change in position, time, velocity, including a change of velocity, and acceleration. Now, why don't we just keep going? Why don't we have the rate of change of acceleration and have something below here in the list? And you can certainly do that just for your education and enjoyment. If you were to take the rate of change of acceleration, that is called the jerk. some people, engineers, have to, when they design things that move people around, they have to minimize the jerk. The jerk is the change in acceleration, and it causes people to have motion sickness and feel uncomfortable. So on roller coasters, they want a certain amount of jerk, but they don't want too much. They don't want people getting sick or, having physiological difficulties because of what they're doing with the acceleration. But everybody wants a little excitement, a little change in acceleration, change in direction, sudden lurches this way and that way. The reason we stop here is that for natural processes, acceleration is usually constant. I believe your book calls it a special case, constant acceleration, but it's true for a lot of different things. For example, if you ignore air resistance and you drop something from a high place, gravity causes a constant acceleration of the object. It gets faster as it falls. It falls further every second, but it's getting faster at a constant rate. Let's talk this through real quick. If you were to jump out of an airplane, okay, I'm going to attempt to draw a stick figure airplane. This is you in a stick figure airplane, and you have jumped out. And we're going to call this the origin, position 0. This pen is not nice. Let's get a pen that's a little better. And we're going to call the positive direction downward in this case. So my number line goes down this way. In the first second, so after 1 second, you'd be going 0 meters per second up here, and you'd be going 10 meters per second down here. After the second, you'll actually fall further, and you'll be going 20 meters per second down here. After the third second, you'll fall even further. See, this gap is getting bigger because your speed is much higher. After 3 seconds, you'll be falling at 30 meters per second. And then we can say down here after 4 seconds, I usually stop after 3, but there we go. You'd be falling at 40 meters per second. So what's happening here is your change in velocity is equal to 10 meters per second every second. So you have an acceleration of 10 meters per second squared. Or some people say meters per second, that's allowed. This acceleration of 10 meters per second is the acceleration due to gravity. And it gets its own special letter, lowercase g. So if you ever see a lowercase g put in place of an a in an equation, you know that they're specifically talking about the acceleration due to gravity. Now, I have lied to you just a little bit. Get used to it. It happens. I shade the truth a little bit when I'm teaching. The number is not exactly 10. Yeah, the Earth is not, and the system of measurement is not so perfect that the acceleration due to gravity is 10. The acceleration due to gravity is really 9.80 meters per second squared. 9.80 here in Los Alamitos. Your book is going to tell you that it's 9.81. And that's because the book was written by 2 University of Chicago professors. And up north, where Chicago is, what's that, about 45 degrees latitude as opposed to our 33. The Earth is not exactly a sphere, so the acceleration due to gravity is a little more. If you just want to leave off this last digit and just call it 9.8, that'll work. And in the AP class, we just use 10. Knowing that it's not exactly right. Like this is good to 1 sig fig, 9.8 would be good to 2 sig figs, and here it is to 3 sig figs. The acceleration due to gravity causes your speed to increase. Now what we're going to get into in this business here is we're going to find out what these gaps are. How far are you falling during these seconds? So we're going to figure out the relationship between time, velocity, and acceleration and displacement. These delta x's, we're going to figure these out as well. That's coming. Okay, that's the next lecture. But let's just finish this lecture by mentioning that, and I'm going to go ahead and hack off this piece of paper and save a tree here, that the velocity we were talking about is really the average velocity. Okay, that's good, average velocity. It's really the average velocity because it uses the total distance traveled in a certain time interval. And if this time interval is long, then there could be all kinds of details going on there. For example, if I was to, okay, let's say I drive to Vegas, okay? And when I drive to Vegas, it takes about 4 hours. It actually takes a little less because I have a tendency to exceed the speed limit, but I'm gonna hide that fact on a recording here. So the first part of the journey between the LA area and let's say Barstow, that's a little too far, but you know, Victorville, Barstow, out in that area. Um, I can't go too fast because there's a lot of traffic. You know, you go through Riverside past the university, you know, freeways are merging, unmerging, all kinds of stuff is happening. So let's just say that my average velocity for that part of the trip, in other words, you know, kind of the one number I could drive and get to Barstow at the same time as all the different speeds you have to drive on a stinking freeway. Let's just say that that's about, oh, I don't know, let's say that's about 50 miles per hour. I know I'm using non-physics units, but this is what you're used to. Um, then, after you get to Barstow, you are free and clear on the 15 freeway, and all the people that wanted to get on the 40 have peeled off, and now the speed limit goes up to 70. And so, Las Vegas, I can average, well, the speed limit is 70, so let's say 70. So my velocity was not constant. And so if I was to take the total distance that it is to Vegas, which is about 250 miles, and divide by the 4 hours, I wouldn't get 50 or 70. And I wouldn't even get right in the middle. I wouldn't get 60 either. What? What are you talking about? Why wouldn't you get 60? You drove at 50 and then you drove at 70. How come the average velocity isn't 60, Harmon? Well, here's the problem. LA to Barstow at 50 miles per hour takes more time than Barstow to Las Vegas at 70. So you spend more time going 50. So the only way to find the average velocity, and this little line on top of it is one way to indicate this is the average velocity. Another way would be to put an AVG down here, is to take the total distance traveled, or total displacement, and divide by the total time. In this case, I would have to say the total distance traveled, well, I should probably figure out exactly what the total distance is given these numbers that I gave you. So, yeah, let's just do it with what I remember. I said it was about 250 miles, and I said that took 4 hours. Okay, 250 cut in half is 125. 125 cut in half is 62.5 miles per hour. So the average velocity isn't the 50 or the 70. It is between the two. Okay, granted, yes, your average velocity is going to be somewhere between your slowest velocity and your fastest velocity, but you really have to go back to this definition. So I'm going to get you to do some problems that I call multi-leg journey problems. And we're going to see how to handle the fact that this is an average velocity. So two things that are coming. One is relationships between displacement, velocity, acceleration, and time. And then the second thing is how to handle average velocity problems. And that'll be our next video.